Thank you. And I want to thank everyone for tuning in tonight. I want to talk about mapping closed depressions using Lidar digital elevation models to facilitate ridge walking, dye trace planning, hazard mapping, resource inventory. Hopefully everyone's familiar with Lidar-derived elevation models, also called DEMs. They're a lot like our beloved topographic maps, only so much better, because instead of 20-foot contours, we have 10-centimeter vertical accuracy. So subtle features on the landscape can just jump out at that level of detail. And tonight I'll walk through some ways to just get a hold of the data, ways to process it, and some useful things we can do with it. And also I'd like to hear, if other folks have ideas of how they've been using it or how they think we could go ahead and use it. Kind of question and answer time. I'd like to hear those suggestions. So many of us have seen some LiDAR images. For the entire United States, we have 3-meter horizontal accuracy and 20-centimeter vertical accuracy for the whole lower 48. And then several of the states have a higher resolution, so 1 meter horizontal and 10-centimeter vertical accuracy. And these are bare earth elevation models. So they basically strip out the tree cover. This lets us see beneath all the tree canopy. They remove the buildings and also the bridges. So if you're using it for flow modeling, the water can successfully flow past the bridges. It's useful for navigation because, well, we can see our roadways. Let me get a laser pointer. Hopefully you can see that better. The roadways show up. Even the logging roads, up here we have a log landing and logging roads. So if you're up navigating on the mountainside, you can run into some familiar features. Fence lines show up nicely. And then we can even tell sort of the cleared areas are nice and smooth, the ag fields, and then the texture areas are forested. The steeper areas may contain outcrops. So for a geologist, that's an invitation for me to go there and look for rocks. For cave hunters, that might be an invitation for a spot where there's some bedrock, so you're not just going into the soil looking for a cave. If you are planning a dye trace, you can find all of the sinkholes and swallow holes for your potential injection sites. Here we have a ravine coming down, probably a spring at the head, and then a little swallet at the end, and another one here. And then some additional sinkholes you might consider monitoring. Sometimes the springs will show up if there's a big enough, physical feature for them. Things like seeps don't. This can also be helpful in terms of what I call digital ridge walking, where you can sort of plan out where you're going to search for caves. You know how many sinks are out there. You know which ones are larger. We can maybe predict which ones are going to be full of mountain stone. And then you also know, whose door is worth knocking on. If they don't have any sinks up there in their woods, don't bother them. Go find the people that do. So if we just want to look at LiDAR, you can go to the USGS National Map Viewer. It wasn't working today. Most days it does. And on the right side, the little stack of paper, you can open up all these different layers that might interest you. And you scroll down to the ones labeled 3-depth. And there's hillshade and slope shade, aspect, a stretched hillshade, which kind of enhances it. You click on the eyeball and that'll turn on that layer. Now you can also rearrange the layers by just grabbing the 6 dots on the side and moving them up and down. And here I moved the imagery to be right next to the hillshade because those were the two I was interested in. And the 3 dots on the right, you can open up a slider that'll change the transparency. So here I have an air photo overlaid with the hillshade. Some of you may recognize this as the Tituna Cave area, Arch Spring area. So that's really cool. It's great for just viewing the LiDAR, maybe grabbing a screenshot or snooping around, right? You don't need to download all the data if you kind of have an area you're interested in. You can view it here. They also have 2 really cool tools on there. And the one is you can draw a profile line. There's a little mountain here. You click new profile, you draw your line, and it will create the profile through the area you drew, complete with elevation marks. And then also there's a 2D, 3D, and you can switch into 3-dimensional view and spin it around and rotate it up and down and really, spy on your neighbors there, see if that's a good site to go visit. Now, on there, you can view 2 different sort of ways of looking at the data. It's the hillshade and the slope shade. These are the 2 I use the most. The hillshade appears to be illuminated from the northwest, which, right, the sun's never in the northwest, but it tricks our brain, and then we can see depressions and we can see hills. The one drawback is things on the south side of a ridge are going to be in darkness. You can reprocess the data to have it lit from a different angle. So the great thing with hillshade, which is what's on the left, is you can see what is a mound versus what's a depression. Slope shade, which is on the right, that is colored by steepness. So the steep area is dark and the flat area is white. I think this makes depressions and other features pop out more, especially some of the subtle features like a very old logging road. And as a geologist, since I'm interested in the steep areas for potential outcrops, I'm going to go right to those dark areas. Now, the drawback is you can't tell a hill from a hole. And I will admit that once I investigated a very large manure pile, but if you toggle between the slope shade and the hill shade or an air photo and the slope shade, you can pick your targets a little bit better. You can also run the model to display the aspect, which is basically which cardinal direction is the slope facing. The topographic position index, which is sort of its place on the landscape. Is it a ridge top? Is it a hillside? Is it a valley bottom? So the National Map Viewer is a great way to just look at the stuff. But if you want to download it, your state may have a digital clearinghouse. But I prefer the USGS National Map data delivery site because the whole United States is in one place. The 1/9 second DEM, that's the 1 meter accuracy. And that's the dark orange on these. So Ohio, West Virginia, Pennsylvania, New Jersey, Delaware, most of Maryland, most of North Carolina, and a smattering of other spots have that higher resolution data. And then the 1/3 arc second, that's the 3 meter DEM, that's the whole lower 48. And it is still really nice. It's still great to work with. So on that site, you then will select your area of interest, either using the extent or the polygon. Make sure you've got checked what data you want, and then just search the products. And in this tab, it'll come up there. You then have to pick that tab. It doesn't pop up. It'll show you a thumbnail of it. You can click footprint and it'll show the area, which is good to make sure you got the right one. If there's multiple in your area, it lists them all. You can either download each one right from the link or add them to your shopping cart and export them as a text or a CSV. And that exports super quick because it's just a list of the things you're going to download. You then copy off of that list, paste it in your browser, and it will download it. That's a little slower. So this tile was a 500 megabyte tile. Depending on your speed, obviously that could take a little bit of time. So what do you do once you get the DEM? You will need a program to process the data. What you get is actually this sort of shaded dark and light based on elevation. QGIS is a free program. I have never used it, but there seems to be a lot of support and tutorials online. I use Esri ArcGIS Pro through work, so it's a platform I'm familiar with. And you can get a at-home personal use only for $100 a year. So you get access to all the tools that I get to use at work for a fraction of the price. You can check your computing requirements right on the website, like it'll check the memory storage and all that, so you can make sure it's actually going to work for you. So now you got the tool to process it, and there is this great short course from the 15th Sinkhole Conference, which was also the 3rd Appalachian Karst Symposium. And Doctor and Wall 2018 published this like step-by-step guidance for beginners. It's like how to add a toolbox, how to add this tool. Once you open this tool, what are you going to put in each box? They walk you through it step by step. Now, it is for the older version for ArcMap, which was a predecessor to Pro, but it works even better in Pro. You can just skip a bunch of the pages. I do have a workflow in Pro that I can share with you. I have to clean it up a little bit, but it's basically just following what they do. It's just a nice little cookbook. They tell you where to download these free toolboxes, which have tools and scripts in addition to the ones that come with the program. You just follow the directions and run them. And this can start to determine all your closed depressions. So you provide the roads layer and the streams layer, in this case, the National Hydrography Data Set, and that DEM you downloaded. And the tools are going to condition the DEM to drain all the points on the landscape. So one of the important parts is going to be passing through roads. They process out bridges, but they don't know where the culverts are, so they don't process out the culverts. And that means that it'll create a false dam, right? It'll say there's a closed depression in this farm field, and you're like, no, there's a culvert under the road. And luckily, the lines and streams are buffered, so they don't need to be completely accurate. You know, anytime we zoom in on this data and the stream's not sitting in the bottom of the stream valley, it's okay. You run multiple iterations of the tool, and it creates an increasingly complex drainage network as it's attempting to drain every point in the landscape. And you run 3 iterations. I will admit some of the drainage is a little creative, like it comes up and over the mountain here, but the mountain drains, we know that. We're interested in the valleys. So once it's done running this, any point that cannot drain, it assigns to be a sink, a closed depression of some sort. And they are shown here in black. You then run an extract tool, and you get all the closed depressions as polygons. You set the minimum area and the minimum depth. So somewhat it'll depend on the resolution of your original DEM. If it was a 1 meter DEM, you're not going to see anything finer than 1 square meter. And the same thing with the vertical accuracy. But if you go too small, I'll warn you, you will see every tree fall throw, every groundhog hole, every spot that a dog dug in the backyard, and you'll go crazy with that much data. If you're working in a big area, so I was working countywide on my projects. If you are just, okay, we got a couple acres, yeah, maybe go ahead and run it. Because, you know, sometimes those groundhog holes have led to some great big caves. Now the results are all of the closed depressions. You had to manually classify them or delete the non-karst. So in this case, I've attributed the stream-related, the alluvial ones, as blue, the false depressions as orange, ones created by humans as yellow, and then things I believe to be karst were marked in green. I did a little bit of field work in this area. For example, up here, there's a storm grate in that closed depression. And this one, I just decided that it was really part of the old floodplain and therefore not a karst depression. Maybe I should have marked that in blue. And there's some that, you know, maybe they're karst, maybe they're not, but it gives you a target to work for. I also toggled back and forth a lot of times, like Google Earth Pro with their time-lapse photography and the old air photos. I found one spot, it was actually the foundation of an old house that was torn down 20 years ago. So on Google Earth, it showed the house, and now I had a hole. So yep, let me just mark that human related. Now the side benefit, if you want to inventory and know the volume of all the quarries in your area, all the in-ground swimming pools, the stormwater basins, or the manure pits, you have that data set. Now, the previous method determined the largest area that's internally drained. So if you look in the upper right, our little Shamrock Depression, it gave just the spillover point for the biggest depression. But you may have a situation where you're interested in the nested sinks. That same cookbook tells you how to get the contour tree tools, how to run those, and it will essentially determine all the nested sinkholes. You get all the contour interval, you get all the contours within it. So you would be able to find the deepest point this way. This is also really good if you're looking for, like, if you have a big sinkhole plain, the entire region, you know, is internally drained. The first method is going to put a big green line around the whole thing, whereas this method would let you see all the little internal ones. So with either method, you can then calculate some important statistics just by running tools. The area, it will calculate. The minimum depth, remember you set this essentially, so my minimum depth was 1 and it's now called at 1.01. The maximum depth, whatever, you know, wherever the deepest point is in that sinkhole or closed depression, it will record that. The range, the mean, the standard deviation, and the sum, which is actually the volume. And in this case, it's cubic feet. And so I feel like here's another case where you really might want to look at the nested sinks. In the lower right, that entire highlighted portion is internally drained. But if you are looking for your dye trace planning or maybe your cave arm waving. You're more interested in that little internal steeper-sided tadpole. So you can use the other technique to get that. You can also get the length of the major axis and the minor axis. So comparing them, if your sinks are all oblong, this may indicate you've got a bedding control or a fracture system control on your sinks and therefore maybe your caves. You can also manipulate some of the statistics. If you divide the area by the perimeter, is this going to tell us how eccentric versus how circular the hole is? Would this indicate how active the sinkhole is? Because in this model, you do get some super snaky, sinuous, closed depressions. And what I've seen is they're either really active or they're gigantic and they subtly, but occasionally flood. And this is, my information is based on Pennsylvania. So keep that in mind. Well, what do we do with all that data? West Virginia used data like that to train machine learning to identify all the sinkholes in the entire state. And you can download that data set from West Virginia and not do any of the stuff I just told you all about. But if you don't like their data set or you're in a different state, you're going to have to run those tools. Here in Pennsylvania, one of the things we have been doing is creating these karst feature density maps. Mifflin County and Huntington County are done, and I'm working on Northampton County. Basically, we took all of those polygons that we decided were karst. We calculated the center point, and then created this heat density map. Now, we weighted them by the natural log of the volume of the sinkhole, because many small sinks don't necessarily equal one large sink. And here in Mifflin County, the data kept being overwhelmed by a single sinkhole. A very large sinkhole, yes. And then we have this, what we call a karst hazard index or a karst feature index. Possibly planners or land use managers, maybe developers could use this to make sound land use planning. Maybe there's areas to avoid because of the denser karst features. Maybe if they're interested in groundwater protection, they might say, these are some areas we need to, take a closer look at. For the land use planning, this sinkhole predates LIDAR. On the left is the Makunji sinkhole. The development had been there less than a decade. And one morning, surprise, nobody can go to work. There's a giant hole in the road out of the development. If we look at the historical air photos, some of you may be able to guess where that sinkhole site is. Yep, the developers, over time that sinkhole had gotten filled up. Developers just built on top of it. With the digital elevation models, they show you even more subtle closed depressions. It doesn't need to be anything as obvious as you can see it from your airplane. And maybe those should be avoided or addressed or over-engineered if that's going to be your new neighborhood. Maybe that's not the place to put your stormwater basin. You could maybe use the data for planning a sinkhole cleanup. You could do a desktop review and provide the field staff with locations to check out, and then combine their notes with your plan. From the LIDAR, you may be able to tell if water flows into it. You can definitely measure where's the nearest road, how how steep is the gentle side, if that's maybe where we're going to set up a haul area. If we want to string rope for a haul system, just from the LiDAR, we can measure how wide the sinkhole is. We can't measure where the trees are, though. I mentioned earlier the dye trace planning. The swallow holes and the sinkholes, whether they're injection sites or monitoring sites. Some springs do show up in the automated closed depression analysis, or others you can just visually see on LiDAR. You can use this data to argue with surface water modelers who neglect the importance of karst conduits. They've sort of said, oh, here's where the water's going to flow, and the dye trace folks can say, no, we know for sure it does not go down there. It goes down this sinkhole and comes over here. If you're into the natural resources, you now have a list of all the sinkholes. You can go and inventory them, see if there are caves in each, see if there are cave critters in each one. This data could be used for flood mitigation. I know some of the other states have, some much more dangerous areas. We do have a few spots that flood from sinkholes in Pennsylvania. Shown here is Phantom Lake in Center County. It flooded in 1936 and again in 72 during two of our more famous hurricane events. It was reported to be 200 acres, 15 feet deep in 72 and 35 feet deep in 1936. Now the topo map shows a 400-acre closed depression. But with LiDAR, you could determine sort of the true area. It probably extends a little bit past that. And also the volume. Now, because this one floods in an open ag area and it has flooded in recent human history, it's not as much of a risk as some of other areas might be. And also now there's a mine right next to it. But if you consider a sink that doesn't currently flood to its highest level, so now in people's memory, they're like, yeah, it floods, but it stops right there. Well, we have changing climate patterns, and we might experience some more intense storms. And the sinks may just not be ready to accommodate that. And we may see flooding unlike we've seen before. Or maybe the sinkhole gets plugged up and can't drain as fast. And so now we do have more intense flooding. The sink on the left is a 230-acre sink in Lycoming County. The topographic map shows the closed depression, but it ends at that north-south road. Clearly, from the LiDAR, it extends a lot further. The road has been raised up to avoid flooding, but you'll notice some of these little tick marks here. We've got some sheds and garages that are down within that closed depression. On the right side is a swallow hole in Snyder County. And usually the streams coming down just go down the sinkhole. But in heavy rainstorms, water discharges from that sinkhole. So knowing the volume and at what flow event would cause the road to be closed, especially if this was an important route, maybe to a hospital or an evacuation route or something. You can hand out the biggest sinkhole awards. Who's got the biggest, the deepest, the largest sinkhole? You can arm wave about how big of a cave could be under there. I mean, that material had to go somewhere. And maybe there's a cave. You could compare multiple generations of LiDAR where they have more than one, and track the changes. And if you're in a place that only has one generation of LiDAR now, I think if you wait a decade, there will be another generation. Like, people from all walks of life are discovering how important this digital elevation model is, for engineering, for population tracking, for hazards, the whole thing. So just stick around and we'll keep comparing, and maybe we can detect a sink opening deeper, or new sinks developing on a trend. And hopefully, at the end, you can help me brainstorm some of the things I might have missed, something that's come to mind. But most important is share the data. If you have run these tools, you can share it with all sorts of users. The simplest thing for your Luddite friends, you can calculate the center point, get the latitude, longitude, export it as a spreadsheet, and they can go out there with their GPS unit and check out the sinkholes. You could sort it by size and send them out looking for caves. You can export it to Google Earth Pro. So someone who uses that platform can view it, drop pins, make pretty pictures with it. But also, if you have processed this through ArcGIS or ArcPro, you can get a free ArcGIS online account where you can host the data and share it. So one tech-savvy person in your group could process all the data, and then they can add the layers that you might want, like the roads, the streams, obviously the sinkholes, we're interested in those, maybe property lines, whatever else your team is interested. And they can share that on ArcGIS online. And then anyone else with a phone or a tablet can download the free app and access your data set, and then they can visit the sites in the field. It can be set to work without cell coverage, which is very useful, number one, for battery life on devices, but also, many of the areas we like to visit just don't have good cell coverage. This is a part of my current project in Northampton County. These are active sinkholes and swallow holes in the drainage ditches in an interchange. And the contractor, the intern, and I could all work on the same data set in different areas of the county on the same day, and then sync our data when we got back to cell coverage. So here are, some of the photos that we took, the locations of the photos that we took on site. And that's also hosted on the field maps. So if we click on that from the desktop, we can see the photo they took in the field. The handy thing about this Field Maps app on your tablet is there's a dot that shows you where you are, just like the Harry Potter Marauders map. So even folks who can't read maps really well, they can still help you ground truth the data, because they can just walk along until their dot gets close to what they're looking for, and they're like, okay, there it is, and now I go over this way. Oh, that's the wrong way. Now I'm going the right way, and they can just watch their little dot. But I can't overemphasize, you do want to ground truth the data. Or if you're packaging it as is, make sure and put caveats in, like how many of them did you visit? Because there's all sorts of other reasons that there's holes out there. I've found old foundations of homes, hand-dug wells, just, man-made things. So I hope this talk gave you some ideas to try out, ways to get a hold of the data and ways to process it. And maybe you can help me think of other uses of the data. So I also welcome questions now. or you can, write down my email and reach out to me directly later.
Thank you so much, Rosanna. That was fantastic.